Welcome to EDU World Space.
All right, so an airplane is moving across the Earth and is moving along it's moving along the circumference of the Earth, right? So along this trajectory here. So the distance traveled by the airplane would be the circumference of the Earth. And this would be 2 pi times the radius of the Earth. And we'll use the actual radius when we're in the final stages of our calculation, but basically that's the distance traveled. And so you have two different reference frames, right? The reference frame of the Earth is at rest. So let's see, Earth at rest would be for Earth at rest, the time taken by the airplane, let's call that T sub b, would just be the distance over the velocity of the plane. And d is 2 pi r e over, and v is just v, which is 13,100 kilometers per hour. And then you have the rest frame, or you have the moving frame of the plane. So plane, which is moving, let's call that T sub p, is the time taken from the plane's frame of reference, will actually be a dilated time because of time dilation in a moving reference frame under special relativity. So it will actually be T sub e, the time measured from the Earth's rest frame, times 1 minus square root of v squared over c squared, v being the same v as in here. And so this is 2 pi r e over v times 1 minus v squared over c squared. Okay. Now we want the difference. Let's go to a new page. We want the difference. So delta t would be the time as measured from the Earth minus time as measured from the plane. And so this is just 2 pi r e over v as a common term, because that is the common term in both those times here, times 1 for the Earth, for Earth measured time, minus square root of 1 minus v squared over c squared for the plane measured time. Okay. And now we use the binomial expansion. And for this, we're going to look at equation A6, okay, which says that 1 plus x to the nth power is approximately equal to 1 plus n times x for x much, much less than 1. And here we have a similar situation. So this is 1 minus v squared over c squared raised to the 1/2. So x is just negative v squared over c squared, and n is 1/2. And this, we can use this because v is much, much less than c, right? C is d times 10 to the 8 meters per second, and v is just 1,300 kilometers per hour. So that so this number is a very small number, so x is much less than 1. So this comes out to approximately 1 minus 1/2 times v squared over c squared. So this means that delta t is, again, 2 pi r e over v times 1 minus, in parentheses, 1 minus 1/2 v squared over c squared. Okay, so the ones cancel, and what you get is 2 pi r e over v times negative 1/2 v squared over c squared. The 2's cancel, one of the v's cancel, and this comes out to be pi r e times v over c squared. That's the difference in time, okay? And so finally, let's work that out. So RE is, you can find this in the book or online, it's 6.38 times 10 to the 6 meters. It's because it's 6,380 kilometers, and the kilometer is 1,000 meters. Okay, and velocity is 1,300 kilometers per hour. We want that in meters per second because meters and second are SI units and kilometers and hours are really not. So 1,300 kilometers is just 1,300 times 1,000 meters. So it's 1.3 times 10 to the 6 meters. And 1 hour is 3,600 seconds. Okay? And so this is what your velocity is. And so this comes out to about 361.1 meters per second. Great. Therefore, your delta T will be pi times RE, which is 6.38 times 10 to the 6 meters, times V, which is 361.1 meters per second, over C squared. C is 3 times 10 to the 8 meters per second whole squared. As you can already see, the denominator is pretty large, so this will be a small number. In fact, we get something very close to 8.0 times 10 to the negative 8 seconds. So a very small time difference. This can be attributed to the fact that the plane isn't moving all that fast relative to the speed of light. And that's it.